All right, so we're continuing with class 16. All right, so this is chapter 16, and I'm going to make the examples separate here. I recorded this already once, and it was way too long. So I am going to re-record this and try to make it smaller because there's no one would want to really see the length of the video. So the topic we're dealing with today is band breaks. I'll talk about disc breaks. Some other things that can dealing with energy and heat transfer, but I'm gonna whiz through them because it was way too long, and we're not going to do any problems with them. So this is mostly what you need to know for the homework is going to be with band breaks. I don't think I'll be asking a disc brake problem or a flywheel problem, but you can continue watching this after we get done with the band breaks if you want to get some more information. So band break types right here. So we have, I don't know if you can really make a band break clutch, but a band break you could think of it as an old-fashioned kind of type of brake. It is a type of brake where we have a piece of braking material. And it could be like steel with the braking material embedded in it or inside, sandwiched inside around the drum, or maybe in the olden times this would be like a leather belt that would be wrapped around to the thing. And it could be fixed at one point and pulled. And the idea here is with this direction of rotation being clockwise here, that there's the friction underneath the wrap of this belt is going to cause a braking torque that's onto the thing. It's going to try to make it slow down or stop. And with the other types of brakes, the main idea here is that we want to try to figure out what the pressure is on the inside and figure out how that pressure is related to the friction so we can see the braking capacity on there. And the way that we do this in a band brake is to take a free body diagram of a small segment of this band. And so we take a little arc of d theta right here and we make it like nice and symmetric right here. And so to the left is going to be the tension over here, and to the right is going to be the tension over here. But actually, it's really just like over to here and right here, because the tension is going to vary along this arc, so that the P1 here with this direction of rotation is going to be larger than P2, because you could think of the friction is pulling on this belt right here as the thing is turning, and we want to apply a tension on here on P2 so that there will be a tension on at P1, but the tension at P1 is definitely going to be larger than that at P2. So we want to try to figure out what those tensions are and how they're related to the braking torque. Right, we want to figure out how, and we do that by how much friction they cause. So we take a little free body diagram. And in the vertical direction, we take the sum of the forces in the y direction. And for whatever reason, they decided downwards was positive. So that, like, if you'll notice that in terms of the angles right here, and I spent too much time on this in the previous video that I decided to abandon, and we take a look at those angles right there, we can see that angle from horizontal here and from here is going to be 1/2 that d theta. Right, because what we've drawn right here is symmetric on each side, so you could do the triangles. You could figure out that that's going to be. So it's in the vertical direction. It's the sine of 1/2 of the incremental angle on each side, and on the left it's p plus dp, and on the right it's p times this right here. And those should really be in the downward direction on this little increment of band. And then in the upwards direction, we have this dN right here, right? That's going to be the incremental normal force that's being placed into this little increment of band. And you notice it's negative, but they decided, I guess, downwards was positive, so this dN is upwards, so it's negative, and it equals 0. Now we make a small angle approximation. This gets done in a lot of things, but the idea here is the sine of a small angle, and it gets small and small and small enough, is going to be equal to the angle. The easiest way I think I can explain that is if we had some radius here. Now, this is not related to this drawing over here, but if it's a radius and we wanted to figure out what this length was right here, we would take the r times the sine of the theta. Now instead, perhaps if that line up here got extended up here, and we're going to have an arc, right? So there would be an arc drawn by that. The length of that arc would end up being r times theta, right? Well, if the theta gets smaller and smaller, that little length right here is going to get closer and closer to that segment length. And if it gets small enough, there's not going to be any difference, really. They're going to be pretty much the same. So that's the idea here. And they just used d theta over 2 and d theta over 2. So what we can conclude right here is that these sines are going to turn into just d theta over 2. And also we'll note that dp, if dp is going to get small and small enough compared to p, that it's not going to matter. So what we're left with is just dn is equal to p times d theta. Does that make sense? Right? That's the small angle approximation that allows us to make that conclusion. And in the horizontal direction, we have we do the same thing. And this time, though, we're going to use the cosine of these two p plus dp, and then we're going to use the cosine of p. But they're in opposite directions. So this one's positive and this one's negative. I guess the left is positive there. Some of the forces in the x direction, assuming left is positive. And I keep pointing this way right here, but I think it's that way for you. All right. Is that right? Yes, the left is that way. Losing it. Okay. Anyway, now we also take a small angle approximation, and for that one, the cosine of a very small angle becomes 1, right? And that's like the same idea up here, that this length and this length, as the angle gets smaller and smaller, they end up equaling each other. So the cosine is equal to 1. So we're able to reduce that down, and we notice that the p's cancel out this time, but the dp does not cancel out, right? We were able to get rid of the dp up here because p still existed, in fact, because they were the signs they agreed with each other, so they didn't cancel out. So they were still there, and p is going to be much, much larger than the differential between them, so we could just ignore it. Down here, instead, the p's cancel out from each other, so the dp still remains significant. And so we end up with two equations right here, and we can equate them. And we can take the integral of them, and we note that dp goes over p, and as we're taking the integral of the thing. And so we know that we get the natural log of p1 over p2 when we do that integral. And so we take that, raise that both sides to the e, and we have this relationship, which tells us how these two are going to be related to each other, right? Between the two tensions on either side, where P1 is always going to be greater than P2. We should mention that out. And down here, okay, so in the previous video, I copied a part out of Shigley, ignore that little segment of words right there, to try to explain this relationship right here. What they're saying is we take another look and try to see equal and opposite, right? So we take a look at, let's take a look at the interface between the belt, and let's take a look at that little gap, an imaginary gap that we could make in there, and take a look and say, okay, there's going to be a pressure that's being forced up against this belt right here, and it's got the normal force over there. So this is going to be dN versus the pressure. Like they're going to be equal and opposite each other, where we would take the pressure that's timed there times an area. And that area would be the bandwidth, that B that's into the page, times the incremental length of this, or R d theta right there. So that's force, pressure times area is going to be equal force, and this is an increment, right? Because it's just a little portion of the band. Well, they're saying, well, you could take that dn and you could take it from up here and you could substitute it, and now we have P. So this is going to be the force at a generic force, generic tension in the belt at any given spot right there. And you'll notice that the d thetas actually go away. So that's where we're saying pressure is related to the tension in the belt at any given point. That would probably be better if you see the next equation right here. But let's just put that on a back burner for a second and say that the torque is going to be equal to the difference between these belt tensions at the ends times d over 2. We could find that from another free body diagram if we took the sum of the moments and we take a look at P1 and P2 right here. And here's the moment arms of those two things. And there's going to be an external torque that's going to be placed onto this thing of T. And so the sum of the moments about there would end up giving us this torque. That's not tension, by the way. That the capital T is the torque. So the torque by the brake is going to be equal to the difference in the belt tensions times the radius, or the diameter divided by 2. And we might want to find out what the maximum pressure is going to be. And that's going to be located right here, right where the belt is touching right where the belt comes out is tangent to the drum and on the tight side. You could also figure out what the pressure was going to be right here. But a lot of times we want to know that maximum pressure because we might be limited by the braking material. If you remember that one table that gives us braking material. So there's an example. So if you wanted to stop right here, as long as I didn't have a disc problem, you probably don't need to see the rest of the lecture stuff. This could be a shorter part of the lecture. So I think this counts as a short lecture if I stop it right now. But if I keep going, I might make it too long. So maybe I need to speed this thing up in case you want to keep looking. So anyway, I'll do this example here in a separate video. I want to start talking about disc brakes and disc clutches. I think disc clutches are pretty interesting. I think I already have these posted. I'll double check on Blackboard. But these are a couple, three good videos to kind of introduce you to what a standard transmission clutch is going to be. It's really hard to tell. This is from another textbook. It's really hard to tell how this thing works. It's a lot easier to see in 3D. You can see that there's going to be this pressure plate that puts up this friction onto the thing, and the pressure that gets placed onto the thing causes the two shafts to join up and rotate together, right? And actually, what the clutch does is actually lifts the pressure plates apart and allows them to spin independently of each other. So then you could change gears, or you could just stop like they're at a stoplight or whatever, and then like engage the thing when you let go of the clutch, and the two things will be joined to each other. But it's a very interesting thing, and I wasted time by showing a video inside a video in the previous recording I tried to make. Disc brakes. There's a similar thing going on here, but now this disc is rotating, and you've seen these disc brakes before probably. I showed a graphic of it in the last class. This is more of a close-up of the thing, and you could see, hopefully you could tell that this is the cross-section part of the disc brake right here. So that's like a part of this right here. And you can also see that there's an air passage in between. You can see what these little air passages would look like, that air can be passing through there to help cool it down. Because that's one of our biggest concerns, is the temperature rise that's going to happen. And we need to dissipate that heat, because we'll see in a second. All of the kinetic energy that's in the automobile or truck, whatever, it needs to dissipate. All of it's going to turn into heat, and it needs to go somewhere, and that could be a lot of heat. So we need to do a lot of things to try to get this brake designed so it will stop and have good stopping power and won't burn up. But we have these pads, right? And these are replaceable, these discs. And So they'll be like right in here. These are the brake pads that are part of here as part of the shoe, and we have a caliper right here. And this caliper, we have a piston, and there's oil inside this brake fluid inside here, and with the increased pressure, it pushes it in here and actuates it and pinches these two brake pads together to stop this. And anything else I want to say about that? Yeah, these brake pads wear down, and it actually has like an interesting like little tab, or there's a couple different methods. I think it's some brake pads. There's actually this embedded piece of metal, and then there's like a little tab that'll break off when the pads get thin enough that like in one of them where there's a metal inside there, it actually will start to scrape onto the sides and make a really loud piercing sound. And another, there's like a little tab that actually comes in, and it gets and that thing is like a little scraper, and it also makes that screeching sound. So if you're hearing that screeching sound, go get your brakes fixed. Anyway, so disc brakes, once again, here's another part of this where it's interesting that it's the management of friction and the determination of that friction based on the pressure distribution. And for a brake, what we find the braking torque in a disc brake is going to be that actuating force times the coefficient of friction times the number of surfaces. In this case, it would be 2, one on one side, one on another. And then we have, we're not using it yet in this equation, the outside radius and the inside radius, and then something called an equivalent radius, right? So that's the one that we have right here for this simplified equation for the torque of the thing, and this is called the friction radius. And then we also have a line of action of a force that we'll see in a second is something that we want to know that determines where should we place this R bar, where should we place the actuating force. Now, the reason why not the reason why, the main thing we want to do when trying to evaluate here is trying to figure out what kind of model should we use for the pressure distribution, because that'll determine how the friction behaves, and then therefore how much torque is being placed in there. So the vehicle by which, no pun intended, of the to determine the torque right there is really this RE. It's that equivalent radius. And we use two different models to try to figure out what that equivalent radius is going to be. One of them is a uniform uniform wear model. And so the best way to think of that is if you were going to put put these forces onto there, and let's say that we put them right in the center. And let's say it wears, let's just think about how it's going to wear. The inside radius right there is moving faster than the outside radius. Therefore, it's going to it's going to wear out faster, right? But it's also going to be where the maximum pressure is going to be located. So it's not going to be a constant pressure across this whole pad, because you're pushing onto the thing, and we have the inside radius is where more wear is going to take place and more pressure is going to happen, right? Over some time, I think maybe the thing would wear out, and then the pressure would probably end up being more and more evenly distributed. But that's not what we're talking. Not over time. We're talking about in the beginning when it's fresh. And then we could have another model where we assume that there's a uniform pressure across the whole thing, right? In the uniform wear, then we decide that pressure is distributed by PA times RI over just the generic R, right? So that's the R anywhere. And so if we wanted to find an equivalent radius, we're really just taking the average radius between there. So it's going to be like the RE, which is not really shown in either of these diagrams. The RE that we would use is really just the midway point between RI and RO. But more complicated thing, I think there is a derivation in the book for the equivalent radius when we assume there's a uniform pressure. So there's two different models, and which is the right one? Well, hard to say for sure, but what we can do is make a comparison of these two things. And one of them is just a straight line. That's the uniform wear right here. But if we have uniform pressure, you can see that uniform pressure is probably going to be a better brake than a uniform wear, right? If we could get the pressure uniform across the whole brake pad, that we'd have more braking and stopping torque than we would if it was large in one spot and then got less and less as you went outwards right here. So that you can see that that's true right here towards the lower end of the D over D. All right, so that's inside radius over outside radius, going up to 1. Of course, that's theoretical. This is just numbers, right? You can't, if they were equal to 1, then they would be super thin, right? But because it needs to have some thickness to it, like how thick should the thing be? Well, we can start to see that as we're going up there. As we're going up, so like maybe they're 1/2 of each other, right? One with the inside radius is 1/2, or inside diameter is 1/2 of the outside diameter. You can see, but anything below that, you can see there's a gap right in here, so that it confirms our suspicion that uniform pressure is going to be a better torque than uniform wear. But you could also see as those two things start to get closer to each other, it starts to not matter. And once again, that's just graphing out these things right here, right? That's the concept right up here. And then we have to ask the question: where should we locate the actuating forces to achieve this? You can see that we take that RE that we find from up here as well, and we place it into here. And now this is the place actually where the angles matter. And by the way, those thetas on the bottom, they better be in radians. There's an interesting thing. I mentioned that this is where dynamics comes into play. We recall that for a rotating body, the kinetic energy is 1/2 the mass moment of inertia times omega squared. Down here at the bottom, I mentioned that we also have for translational kinetic energy, and we'll have, in like a car, we'll have both, probably more translational energy than all the rotating parts, like even, you could even say some of the engine, but really probably thinking more along the lines of the shafts and the wheels and maybe the transmission, but you could think of it in those terms. All the things that have to rotate, let's say, when you're not having external energy be applied. So like, let's say that the engine isn't like supplying the energy. Let's say the clutch is declutched, right? And it's just rotating through. So not the engine, but all the rotating parts are going to have a kinetic energy, but also the mass of the car itself times the velocity of the car. So we wanted that, all of that needs to go into the braking, and that will all become heat right here. So if we're going to apply, now we're going to connect dynamics with heat transfer and thermodynamics, but mostly heat transfer. So we could try to use that to try to think of how the temperature is going to increase in the brake, right? Or in the clutch, right? The clutches burn up too. So I talked too much in the previous recording I tried to make of this and abandon it. I talked too much about units. Units can get really messed up, all right? So just be on the lookout for them. I don't want to spend a lot of time trying to get these straight, because I think I just confused myself last time I was talking. So just have to be very careful. A lot of times it's almost worth your while just to stick with SI, because we have various things that we have to worry about. And do I divide by gravity or not by gravity? And then do I use the thermal equivalent of mechanical at work right here, or the mechanical equivalent of heat is the 778 foot-pounds per BTU, something that you have to use to connect them. In SI units, we go joules are the same thing as a Newton meter, whatever, so we can, it's pretty easy to jump back and forth. But US units just inherently screwed up. I do an example I'll record the example, but I don't think I don't know if it's worth it. Maybe I'll just do it for posterity, but I don't think I'm asking a question on this. I haven't talked to Dr. Orlup yet. Now, here's a tough one. All right, so the book doesn't do a great job. I looked through a bunch of different resources. I really wanted to have a problem a couple of years ago where I tied all these things together because I really like that as part of an idea for the class, but implementing it has all kinds of snags. So the variables that we deal with here, and I think I actually have something wrong here, and I got kind of angry at myself. Use the specific heat of materials, right? A lot of times we think of specific heats of like fluids, but you could also have specific heats of the materials themselves, and then the mass of those parts. And then this is, I don't think this is true right here. I wouldn't say the heat rate, right? Because the equations I have at the bottom are not heat rates. There's no time inside either of them, so I shouldn't have defined that way. We have the theoretical temperature rise, which is really the thing that we want to try to get. By the way, my arthritis is killing me. And the theoretical temperature rise that we might have. So this is a very simplified heat transfer type of equation. There are no partial differential equations in here, right? So we have the environmental temperature, so that's going to be like the heat sink, right? The air out there, you can't heat the entire world up. The maximum temperature, and in doing any of these calculations, if you were to actually try to get values out of this, you'd have to take them with a grain of salt, that they would be very much an instantaneous temperature. It would be a temperature at a very small point, and maybe just a little distance away from it would be a much lower temperature, because these maximum temperatures are going to go crazy high as part of that. That's one of the reasons why I didn't like doing these problems. Now, this is Shigley's method. They're just breaking down the overall heat transfer coefficient, which I'm assuming that you're familiar with. They're doing it in their own way, where they're breaking it down into radiant and convective. And then they're also putting in a factor inside there, right? So, and they're doing it from this figure 624, which is on the next slide here. So they're taking surface area. So here are those coefficients that they're providing. You really want to take these with a grain of salt, right? But you see that the coefficient, the heat transfer coefficient, is a function of temperature. So instead of just looking up one particular value in a book, they tried to do a little bit more technicalities, try a little bit more closer to realities. You know, the heat transfer coefficient is a function of temperature. You could also say that there also is reliant. The convective one is reliant on the fluids and the film developed around the parts, and so that they just have this simple modifying factor right here for the forced ventilation, so that it's a function of velocity. So you'll see back up here, they're saying if you want to get the heat transfer properties of this piece, here is a way to try to estimate it. I also mentioned that it is dependent on the surface area. There's also the time that it's been engaged. Here's the big problem, is that the actual temperature rise will depend on lots and lots of factors, and these ones that we're doing here greatly oversimplify them. And also another aspect is that braking is often applied in pulsations and not this constant thing, because the temperature gets too high. Brakes will burn up. There's been years and years and years, more than 100 years, obviously, since some of the first cars were invented, for them to improve and improve and improve upon this incrementally, and then just sticking a simple equation out of a book and trying to come up with numbers that make any damn sense is really sort of like, it just ain't going to happen, right? So we do want to understand the nature of the brakes by seeing these equations, but actually trying to calculate the actual the numbers with them is sort of a mistake. But Shigley does try to do that anyway. And they get a maximum temperature, and I've run through this. I was hopeful that we'd have like some interesting things, but the numbers just become out ridiculous. So I'll see. I can't remember if I have an example. If I have, I will make a video where I go through this. And once again, for posterity, it's not, I just don't, we don't have enough time this semester and previous semesters. It was almost a little too ambitious to even include these topics, but I thought they were very interesting and I had the best of intentions. So, in another book by Tyler Hicks here, the Handbook of Mechanical Engineering Calculations, it's a very straightforward book where you're using these kinds of simplified equations. I'm sure that they are big fans of Shigley, and Shigley a big fan of Hicks. As it's the kind of like, meat and potatoes kind of mechanical engineering calculations that could be really useful to you as a first pass, but not for the designing of a brake, not even close. But the actual temperature attained by a brake drum and the time required for it to cool cannot be accurately applied. We can end a period right there. Just, make that statement. But the method here is suitable for preliminary calculations. In the final design of a new brake, heating should be checked by a proportional comparison with a brake already known to give good performance in actual service. So you need experience to be able to actually design with the thing. There's not a cookbook formula to say, okay, here's how you apply these basic principles of dynamics and heat transfer that will give you an actual answer that's useful. And then I had an example where I went through there, and you could see with my Honda Pilot. I drive a Honda Pilot. I'm a big fan of Honda Pilot. You can see what that temperatures become in that example. And the last topic I think I have in here is flywheels, and the purpose behind them is to store energy and to smooth out a ride, right? So you remember in our single-cylinder engine that there's a power stroke every other rotation, and that power stroke's only 1/2 of that rotation. So there's 3 more half rotations that are needed to go around for that one half rotation is the only time where there is actually some kind of like real impetus for it to go around. So to be able to smooth out that really herky-jerky kind of a load that's being placed onto the thing, you need a flywheel. And you remember the flywheel we passed around was a big old chunk of cast iron, and it needs to have a sufficient mass. And you try to figure out, well, how do I figure out how much mass? Well, that's the discussion that's part of Shigley right here. We go through the idea of the energy, or a incremental energy, delta U they're using here that for a generic energy, is the torque times the delta theta. So, hey, remember what we had when we were able to generate a torque curve right here, right? Or something like that, along those lines right here, where this was theta and this was torque. They're saying that energy is torque times d theta. So the energy, the area up above and the area below right there are going to be energies, and one's going to be a positive energy and one's going to be a negative energy. So here they're showing here they're having torque versus theta. But we also can have, and by the way, the torque, the area under there would be represented by the energy. We could also superimpose the angular velocity. So you'll also notice there's an omega right in there. So the angular velocity will also fluctuate with the angle, right? So that's really the thing we want to try to do, right? We want to try to keep that angular velocity constant. We also would like to have the torque constant. So we see that these things are related to each other by the kinetic energy. So the method by which they do this in Shigley, or in other books too, every time this topic comes up for flywheels, we have a coefficient that we use to try to describe the smoothness, and that's of the rotation, where it's going to be the maximum minus the minimum divided by the average, right? So if you're fluctuating right here to the thing, right, we tried to categorize how bad is it? Is it like this right here, boom, 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 or is it like this right here, or is it smooth, right? We want to try to get some type of categorization of that. Here's some suggested values of that CS, and this is from a different book. Where you can get kind of an idea of what that would mean if you used a CS. here is where we have the delta energy that we would find after we started piecing together these torques right here. Would try to give you sort of an idea of how that the torque energy is related to the kinetic energy right there. The difference between the top here and the bottom. All right, so we'd get the energy difference we'd integrate the energy in the top, integrate the energy in the bottom. We see what those differences are right in there, and then we see what the average rotational velocity is, and then what our desired S is going to be would be to help us to decide how big this I needs to be. That's the big idea. And so without that going any further into that, I'll see how long this video is. It's probably still too long, but I tried to put together something that would be useful, that would combine all of these topics and also combine other topics like dynamics and heat transfer. It's kind of an interesting thing and a practical thing, but also shows you some of the limitations. Now, for guitars today, I'll say for hats today, you can't really see, but that is a black on black Buffalo Bills hat, right? And then we're wearing for shirts, we're wearing the Larry Bonin band, right? So Larry is the bassist of the band, even though I'm the singer and guitarist. And Larry looks kind of like that right there. I took a picture of him and I traced it. But that's the Larry Bonin band. And it's funny because everybody knows Larry and everybody could tell who Larry is. So for guitars today, we have a replica of the Van Halen guitar featured on the cover of Women and Children First, which is the third album. Now, the original guitar that this is based on is the Van Halen. He butchered a guitar that was a pretty decent guitar. It was a copy of a Gibson Explorer. It was actually, I forgot the name off the top of my head, but it was an Ibanez. There's a name for it, but they made a copy and they got sued by Gibson. But he had one of those, and he decided he wanted to cut this notch into it. Right? So the notch is usually not here, and I believe that he drilled a bunch of holes, even though he claims that he chainsawed this out. And it started to split up the middle. So he put these turnbuckles in place, and he thought it looked kind of cool. But then he took his bicycle paint and he took a bunch of, he sprayed it silver, I believe, first, and then he put a bunch of tape on top of it and then spray painted red on top of it. And it was bicycle spray paint. I don't know what, do they even make spray paint that's specifically for bicycles? But that's what they've already said. And you see that it's got this hockey stick looking headstock to it. But it's a pretty cool guitar. I like it. I like the looks of it. It's not like something I would actually play out in a band. So there's some more ME470 content. The end. Discard all that, and let's see what was the damage. How much time did this take? Oh, I'm going to get rid of you. 38 minutes. That's too long.